Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon. My name is Alisson Sol, and I'll talk today about our web attack detector that we are developing in partnership with Azure. And unlike Pensheng, you will see that I cannot stand still, so I'll move a lot. So this is a partnership, as I said, with the Azure Security Data Science team, and they have been developing this with us for almost a year now. And we have developers on both sides. And it's very important, we have access to data from both the Bing usage logs, the Azure portal logs, and the VSO request logs. So this is a lot of data that we use to train and to verify the web attack detector. Our specific team, the Bing Shared Services team, also offers some of the services that we do as APIs. So we have an API that, given a URL, gives you the reputation information that we have, another API that tests your site for accessibility issues, and one API that, given a URL, we attack that service for you and try to find vulnerabilities before others. We test your website for vulnerabilities like cross-site scripting, SQL injection, and others. And this is a service that, hold on to this name, WebSec, because it will come back in this presentation. So the problem that we are trying to face is basically this. For Bing, for example, we have a website that receives requests from customers. Customers come to us to make requests about all the data that we have, which is syndicated content, social media graphs, cat pictures, and some ads that we serve to get some money. And basically, a request is something like people go to our website and try to solve huge problems. Most of the requests are very benign. It's people trying to do good things and search for answers to those problems. What happens in the back end is that we get this request as an HTTP request that is having some parameter value, the value that comes from this request from the customer. Indeed, we log a lot of data. This is a simple example, and we log even more data about the session, about cookies, headers, and lots of other information from that customer request. But for the sake of simplifying and not showing to you in every slide the entire middle bullet here, I will just stick with the final bullet here for the examples. But remember, what I'm talking about here, indeed, in reality, there is a lot more data for each request in the backend. So what is to verify that a web service or website has vulnerabilities? Basically, you get those parameters that your service accepts, and you inject attack strings. There are websites like the OWASP project where you can go and learn about attack strings. And in this example, I am looking at the query parameter and inject one attack string that, if the site is vulnerable to cross-site scripting, will have some behavior. And of course, hackers will do this, encoding this attack string. It is not very easy to read the request that is a real attack when they do it. Luckily, in this case, Bing is not really vulnerable to the cross-site scripting, reflected cross-site scripting, and it just kind of returns that information without any problems. But the real attacks are far more complicated. This is a real attack, and later you see how we found it. But basically, we go through this billion of requests in Bing, and we find these things that it will take a human a little bit of time to, is this an attack or not? So we could let people attack us. That's not a problem, especially if we are not vulnerable, if there were not other consequences. One is that from time to time, someone deploys code that has a vulnerability. So you find that vulnerability, and you are hoping that you found it before someone in the outside. The second thing is that there is some capacity in the system that is being misused because of this. When you are kind of doing the anticipation of all the capacity that you need for a service, if 50% of the requests will be attacks, you are wasting a lot of your capacity. Also, you cannot just say, oh, I found, it is that user, he's sending me a bad request. Maybe his machine is infected and he is kind of just one of those botnet participants, and I cannot just say, oh, that IP is sending me a web attack, let's block it. And finally, we are likely having attacks that we are not finding, they are succeeding in we don't know about. So what can we do? One of the simple things is let's try to increase the cost for the attacker. Let's do something as simple as if I suspect this web request is an attack, I delay its answer for 1 second. For a real customer, probably that's not a problem. You probably have waited for 1 second on the internet at some point in time, and that's fine. But for an attacker, I just limited his ability to attack my service from 600 attacks per second to 1 attack per second, 86,400 per day. So that may definitely increase the cost. How can we do that? We do a lot of offline analysis already in our sites. We, of course, have these logs. We do the log analysis. We create attack reports that include which is attack strings, like what you saw, and we'll see how we do this, and also IP addresses and all those things. Ideally, I should be able to create a module that will do this at near real time, so I can create a web application firewall module that I put in front of our website. Logically, doesn't really need to be in front. Maybe it's just a model that is called in parallel. And then that can be that additional cost for the attacker where his request or her request takes 1 more second. How can I do this? One of the approaches is using regular expressions. That is the approach that we are using in partnership with Azure. Indeed, Azure is using in partnership with us because they started first and they did 99% of the work in the regular expressions. So basically, what is that you need to do? You, as a developer, if you know regular expressions, and some of you may know, you can try to look at those strings and find patterns that will detect that the request is an attack. And you find one, find the other, and keep going. And as you can see, our partners are doing a fantastic job on creating these regular expressions. The other approach, which is a different approach, which is the one that we try to do, and we are also working on cooperation with Azure, is you have ground data, some data that you know that has attacks and non-attacks, and then you create features from this data, or attributes or properties or whatever name you give to this thing, and then from that you do training for a machine learning model, and then your model will get your request at runtime, extract the same features that you used for your experiment, classify or regress this and give you a probability that this request is an attack. And you need to have a scoring process, which will then tell you, hey, that was an attack, you detected. That was not an attack, you didn't detect it. Or the bad things are the false positives and false negatives, when something is an attack and you miss it, or false positives, you say is an attack and it is not. Each method has its pros and cons. So basically, in the case of the regular expression, starting up is easier. So it was easier to start this process. You add the first rule, it's working, you add the second, and so on and so forth, and you go. You evolve, you have steady progress, because if you try some rule, it didn't kind of work, what you do? You go back. So our partners on Azure, they have this continuous testing process where every day they see if there are no regressions, and if something made things worse, you go back. But there is a cost of this, which is at the runtime evaluating regular expressions. Any of you who have experience with regular expressions know it is very costly. Regular expressions cost a lot of time, so you can have a single regular expression that costs you 350 milliseconds at runtime, and that adds up if you have a list of regular expressions, and then soon you are taking a lot of time to evaluate if the request is a web attack or not, and the biggest problem maybe it is that your worst case, it is the benign request. If the request is good, it means it has to go through all those tests, fail, and then you say, oh, it was not an attack recognized by those regular expressions. Well, what about the machine learning approach? The machine learning approach, if you use the proper method, and if you find the right features, as we will talk about, the key is finding the right features. If you use the proper method, then you can have a very good runtime performance. There are ways to, whoever is an expert knows, we can prune trees, we can do a neural network with so many layers. You can guarantee a runtime performance, depending on accuracy goals, and you will have the evolution from your data. You can make the system evolve from your data. But the biggest problem is that starting up is very costly. You have both time that you need to invest in and people and a lot of effort on tests that will give you those right features. And the second thing is that progress is not linear. With machine learning, one of the biggest problems that I had in all the machine learning projects that I worked is people saying, oh, you are at 90%. When it will be at 92%? You say, I don't know. And that is a frustration that a lot of people that deal with machine learning carry on, which is you fail, one day you succeed, oh, I'm at 95. But it's fantastic that you can even have regressions. Indeed, I asked one of the top experts on the field, who I happen to know, Christopher Bishop, who is one of the top experts on pattern recognition and machine learning. Indeed, this is the name of the book that he authored, which is the classic that everybody reads about machine learning. What was the top challenge for machine learning? And on the long term, he says, it is basically that machine learning arrives at AI. But in the short term is how we can do machine learning without that much labeled data. How we can use these unsupervised methods, as you probably have heard, to really progress machine learning without the cost of labeling. And why? Why would someone say this and not say that the methods of machine learning, you see, he didn't say that the biggest problem is SVM against trees or trees against neural networks and all these things that we see a lot of people wasting a lot of time in these discussions. It is because labeling is extremely costly. Suppose that I have 100 billion requests per day, and it costs me 1 second to label each one. I have this expert that can look at the request, that long request that I showed you, and say in just 1 second, this is an attack, this is not an attack. So I need this labeled data to train my system. Well, with 100 billion requests per day, if this person works just 8 hours per day, and it's kind of keeps performance, 1 second per label, it will take just 9,000 man business days to label this data. And if I find 200 of those experts, it takes just 47 days. So after 47 days, I label the data for 1 day. Obviously, that is not a very scalable approach. So the other thing, whoever labeled data here knows it is that people make mistakes, isn't it? So you have all these books and articles that you have to read about how to have multiple people labeling the same thing, and you get 3 people labeling the same thing, and if 2 disagree from the other one, you have the minority report. So, okay, I had to put that there. So the other thing is that when you are doing data capture, you will have gaps in your data. So I use this system to watch movies that most of you also use, and they give me some recommendation of movies. And right now, for example, at a certain time, they recommended that I watch Strawberry Shortcakes, and also Doctor Who, and also Spiral, a French series. But why? Why they do this? Because for a long time, they captured data about movies watching on my house without asking who. So the data just say, it's Allison. But my daughters were watching. So now I have this very strange kind of taste. Whoever knows me knows that I have these strange tastes. I keep watching Strawberry Shortcake. The other thing that is very important is there is no such thing as data capture without a model. This is very important. A lot of people that I talk with and they say, I'm data-driven. I say, okay, cool. I'm really, now I will have these metrics about the performance of developers. Okay, cool. And what are you capturing? And they are capturing this. And what's your model? I don't have. That is not to be data-driven. So in what is probably the only story that we will remember 5 years from now from this presentation, I will tell you this. When I was a child, I was born in Brazil, not on the beaches, but on the country. And my grandmother, I lived with her for a year. And my grandmother, he is from a kind of indigenous tribe. And basically, I never had medicine until I was probably 10 years old. Because you get a cold, she takes you to a healer. He looks at you, he thinks there is this spirit on you that's making you sick. He smokes something from several different pipes, and then you are cured. Amazing, isn't it? That's probably why I don't get sick as an adult. I never had medicine until 10 years old. So the fantastic thing about this is, if I'm doing a machine learning model, and I tried this when I was a child, I was enchanted by this. This guy, he smokes a pipe. So probably I need to think, I come with a code, there's pipe on the left. So the data that I'm capturing is totally dependent on the model that I have on how the things work, isn't it? Now, there was this other guy a few decades or centuries ago who was doing something totally similar. You probably have heard about this doctor from Hungary that was kind of in the hospital, and the doctors, when they made deliveries, there was this very high death rate for both the babies and sometimes even the person delivering the baby. But when midwives were doing the delivery, the rate was low. And he started to capture which kind of data? Who was doing the delivery? And if they were washing their hands. And then when they found that if the doctors were washing hands, the death rate would go from 18% to 2%, he came up with this theory of germs, okay? And you know the conclusion of this. The doctor said, this guy is crazy. He's telling us to wash hands. He died at 47 in a hospice. So the thing is basically this. Even if you have the right data, and if your data is complete, you still need to have a model. I'm repeating how many times this. Data-driven means I have a model that allows me to understand my data. If you don't have a model, just capturing data is useless. So suppose I have a model for me to have the price of houses based on square footage and the number of beds. So for simplification, of course, here I have 2 groups, and I have a new house here that I want you as humans to think. Which group do you think this house is closer to? Well, most of you will say the second group, the group that has houses with bathrooms. Most humans consider bathrooms in houses kind of a convenience. Now, one of the machine learning methods that most people have heard is, I group my data using k-means, whatever, I calculate the centroid for that group, and then for a new data point, what I do? I measure the distance to the centroid, and then I classify in that group. If you do this for this particular new house here, it is closer to which group? The first one. Mathematics will never fail. Why? Because there is one feature that will overrule all the other features. The numerical values are so much bigger. I need to know how to model this feature. So I need to have a human that tells me, well, typically houses go from 500 to 500,000 square feet, and bedrooms in the house go from 0 to 5. Scale and normalize your data within these ranges, and when you do this, then you see what? The new data point is far closer to the second group. Unless you already have a system for what is called deep learning, there is no way to derive this from your data, because you will have to have a human to tell you this, or the system will have to learn this from the data. And that is the goal of these deep learning systems, to learn both the features and how to normalize them directly from the data, but we are not there yet. So I have all these problems. I have incomplete data, I have wrong labeled data, I have wrong features. Suppose I didn't have any of these problems, which we have, by the way. Now I have those features. How do I go to that distance that I just calculated there in the houses? You remember, I calculated distance using Euclidean distance for those people that are more mathematically inclined. And, but that is something that is not always correct. And the biggest problem is I need to create features and I need to calculate distance based on strings. Strings and other properties that are like this. So I ask you, what is the distance between the first and the second strings there? Anybody? You are the top 30. Directly 30. You know? Anybody calculated? Which distance did you use? Levenstein or what? So see, this is extremely hard because all the machine learning methods are based on distances and numbers. It doesn't matter if it is regression, if it is k-means, if you are trying this maximization, minimization. I need to transform these values that I have, which is mostly strings, IP addresses, into distances, features that have numbers, and then I will be able to, using a model, really classify those things. So what you need to do is to think like a freak, which is the title of the new book from the guys who wrote the Freakonomics book. Very good book, this one. And basically, you have to start testing. Is the URL length somehow correlated with being an attack or not? Is the number of keywords like script or something? Is the number of symbols? Is the string distance in the sense of Levenstein distance something that really makes sense? And what we did is a lot of experiences, and we are still doing this. And we developed code that calculates numerical values from those strings. For example, here is some code. So since we focus on the parameters and the parameter values for the attack recognition, for example, I need to know that, see, I have two, in the first test, I have two sequences of values for the parameters, and it gives me the distance 4. Here I have the parameter value just changing from which parameter it is. The distance is still 4. And finally, here, I have this parameter value changing, and yet the distance is 0. So this is the kind of code that you need to develop for you to be able to transform those attack requests or those requests into parameter values attributes that will give you the features, and then you will have the final measurements that you can use. For example, you also have to consider your model. In this case, because people will encode the strings, our code And this is code that takes just 1 millisecond. Those 3 strings, the distance between them is 0. So it takes an enormous amount of time for us to do what? This code. After you do this code, the machine learning really comes naturally, but who would think in the beginning that this was the hardest code for us to develop? And finally, both for our attacker and for the one from the Azure data science team, how do we test it? Remember I told you to hold on to that WebSec thing, the WebSec application and service that we have that attacks our services? Well, if I have web service, and if it is attacking our own service, I have something that is very important, isn't it? I have attacks that I know they are attacks. I know when to search for them in the logs. So I have several positives. And because attacks are something precious and I can defer those from the other normals, I can then do the scoring. I can kind of, both for our and for the web attack detector being developed with regular expressions, we can kind of, well, let's start with a sample here of 7 million requests. And I know, because I really prepared this data, that 3,459,512 and 512 are attacks, and the others, I don't even need to know perfectly that they are not attacks. I just need a mix that allows me to start this process, isn't it? Because I can evolve. And then what I do is I run through the recognizer and I see how many it detected as attacks or not attacks. And then if the 2 flags are equal and they are 1, I have the true positives. And then I have these negatives and so on and so forth. This allows me to calculate what? My precision and accuracy. And then you see that, for example, this is the regular expression detector. It has a very good accuracy that in most of other fields would be already perfect. But when you have billions of requests, you need to still continue improving. And how do you continue improving? Now you need to take a look at those where, let's start with the ones in which we differ, the opinion from the source ground truth and the recognizer is different. But you need to classify who is the volunteer to go through 118,330 URLs and each one tell us if it's an attack or not. Well, what we did is we created an application that, using that same distance calculations and all the attributes and features that we found to helping our machine learning system, we can group the data. And you see that in this case, I simplified for just 3 groups. You see that the groups, they look like each other, in between the group. Those are the 3 best groups of this. And you can change the number of groups, and then you can label again. And with this, you have the feedback loop that you need in all the machine learning processes. And we also, our intern this summer, got this application and made it into a Spark-based application that runs on the Azure HD Insight Spark clusters, and then you classify directly blobs in the Azure storage. And this allows us to continue our machine learning training. It's not as good yet as the web attack detector or the regular expressions, but it's evolving. We can do web attack detector validation, and we can identify new attack strings, as I showed you in the beginning. What is the future for this? We will continue with our machine learning training. The regex team is continuing to improve. For example, we started more with regular expressions for XSS. Now we added SQL injection and so on and so forth. And our ultimate goal is that in a few months, we have a microservice, something that is in a container that we can just give you, and you can use it in your solutions. But in the meantime, if you have any application for this, just contact us in this alias, and you can reuse any part of our solution that applies to your problem. Thank you, and